year, celebrate Daniel's birthday. Daniel has helped many people in Latin America. Was instrumental in bringing the next FQ to Brazil. It's helped a lot the embryo, let's say, of the organizing committee to bring this meeting here. So thank you, Daniel. Of course, as a researcher, I consider him giant. So happy birthday. So my talk will be about some types of evaluation codes. So let's start by establishing the notation. Also, let me apologize for. I know there are some people here that was in the Brazilian Algorithm weeks ago. I'm sorry, it's the same talk. So FQ is a field of few elements. We know that the code of Fn is just an FQ subspace of FN. And of course, the vectors of the code are called code words. We know that given in totals of leading FQ to the n, there's this n distance defined, which is just a number of positions where the encompasses have distinct integers. With the minimum distance of the code, it's just the minimum of the distance between two distinct code words. Since the code is a vector space, this is also calculated the distance of line to 0. So in the end, we just want to calculate the minimum of the distance of non-zero code to 0 and the distance of non-zero code to 0. It's called the weight of the code. So we all know this. So the problem is how to define codes. So if you ask a student of linear algebra, he'll say, "Oh, it's very easy, just pick a set of vectors and that's it." No, it's not a bad idea, but the thing is that if you do that, it will be very difficult to determine the minimum distance, even using computers, even if your code is defined over FQ. So what people do is, of course, there are many approaches to this problem. Frequently, we see codes built from geometric or algebraic structures in a way that using properties of these structures, you can determine the length. Usually it's easy, the dimension is not so difficult, but especially the minimum distance. Or if you don't succeed in determining the minimum distance, maybe you will succeed in determining a lower bound, for example, for the minimum distance, using properties of this structure. So the concept we will present in the slide to go to this last so-called affine evaluation codes. But the idea is to start with a subset of an affine space of dimension n over FQ. So this is just a set of points we want to be in, and I know by this I sub x the vanishing ideal set x, which means the ideal from by all polynomials in this polynomial unit, which are 0 in every point of x. And the evaluation map, which goes, let's define this evaluation map psi, which goes from these functions to FQ to the m, and you take a class of a polynomial and you make points. Of course, this is well defined. This is clearly an FQ linear transformation. So in this talk, this quotient ring will be considered as an FQ vector space. So this is an FQ linear transformation, and actually is an isomorphism of FQ vector spaces. And given a subspace of this vector space, so the image, of course, is a subspace of FQ to the m. So it's a code according to our definition, and this is the evaluation code associated to L. Of course, it has length m, and if you know the dimension of L, the dimension of the code will be the dimension of L. Psi is an isomorphism. Now I will present some results from Gröbner basis theory, which will be used on flows. So we developed by this script m, this set of monomials in this polynomial ring. Of course, we remove the product of powers of variables, where Q is a field, K is a field, We invite the set of monomials with a monomial order. So what is a monomial order? It's a total order such that 1 is the least monomial. And if you have an inequality, you multiply the inequality by the same monomial, and the inequality still goes. So this is called monomial order. The set of monomials. Okay? So now, of course, a polynomial is a sum of non-zero polynomial is a sum of monomials, also with some coefficients. So since we have a total order, one of these monomials must be the greatest, and this greatest monomial is called the leading monomial. Now, let I be an ideal polynomial. We say that the subset G1 to Gs of I is a Gröbner basis for I with respect to some previously fixed order. If the leading monomial of any non-zero polynomial I is a multiple leading monomial full of difference. So this is a Gröbner basis. Okay? We have to fix an order because you were talking about leading monomials. And you can prove that such a set is a basis for the ideal in the usual sense of set of generators. Gröbner basis appears in the thesis of Gröbner, and his thesis problem was to determine the basis for this quotient ring, of course, considered as a key vector space. Of course, we know that, but he showed that such a basis is given by classes of monomials. Monomials in this set. You take a monomial which does not appear as the leading monomial of any non-zero polynomial in the ideal. If you take the set of monomials which do not appear as leading monomial of any polynomial in the ideal, you take the classes of these monomials. This is a basis for that quotient seen as a key vector space. This is problem, long-standing problem, is advisor of Gröbner. Gröbner had already worked in this problem for more than 20 years, and then he gave it to a student. Actually, Berger solved this problem in 1 year. So, of course, at the end, in his paper, he called those G1 to Gs because he proved that any ideal meets the Gröbner basis, and in the original paper, he put out standard basis, but then 10 years after, he decided to call that Gröbner basis because he felt that he owed many of his ideas to ideas of Gröbner, which he had learned in seminars during his years of student. So he proved that any ideal, if you fix any monomial, you can determine an ideal. Of course, we know that. He also produced an algorithm, which is called Burgers algorithm, that starts with the generating set to produce the base. And what our interest is in this set, the footprint. And it sees that there's a very close relationship between this set and the basis, which is the following. If you have a basis for the ideal, then a monomial is in the footprint. If and only if the monomial is not a multiple of the leading monomial. So this is much better because of the definition of footprint. We have monomial which does not appear as leading monomial. It's difficult to verify, but this is very easy. If you have a Gröbner base, you just take monomial, not a multiple of any of these guys, and you already know the footprint. Okay, so now let's recap and modify a bit that you represented so far of construction of codes. So now again we start with X, subset of fine space, vanishing ideal, S of X, and now we take this set of n non-zero elements of FQ. And we define this new evaluation morphism phi, which is an evaluation morphism as psi was, but we multiply by this numbers, non-zero elements. Okay, so then we still have that phi is an isomorphism of FQ. Footprint we still have X. We know that the classes of these monomials form a basis for that quotient as an FQ vector space. And an important consequence of the fact that phi is an isomorphism is that, of course, the dimension here is the number of elements in the set. The dimension on the other side is n is the number of. So this is a typical algebraic geometry equality where you have an element that comes from algebra and an element that comes from geometry, each on side of the box. Now we will produce our code. So we take A to be a subset of this set of monomials. This now is the expression of code. We take A to be a subset of this set of monomials. We take the class, you denote by this script A, the subspace of the quotient generated by the classes of these monomials. So the image of this script A is the generalized monomial code associated to A and B, which is denoted by CAV. Of course, it's a focus like n dimension of the number of monomials in the set A, and we are interested in studying the dual of these codes. So this sort of explains why we multiply this. So for those who have some experience in coding theory, you know that the duals of Reed-Solomon codes. In the dual of Reed-Solomon codes, you have these elements that appear. This motivates this definition. Okay. So now, but we now will start this. All these results from now on appear in the paper, which is published this year in the bulletin. If you want to just. So assume from now on that I sub x is not any ideal, any vanishing ideal, but at least a Gröbner basis with respect to some feasible order with the following properties. So the basis has n monomials. So n, recall, is the number of particles. And the basis has exactly n monomials, Gn, and for all I, we have that Gi is a polynomial EFP x1 to xi. Okay? One may show that since the footprint is finite, the leading monomials of G1 to Gn must be of that form. This is something very easy for if you have some experience with footprints. So the footprint, if it's finite, must contain powers of all the variables. And from this condition, it follows that the leading monomial of Gi is xi to di. For example, you know that the leading monomials of this basis is of this form. You know that only Gn has the variable xn. So the leading monomial of Gn must be xn. And so on. Okay? So this is easy, and from this we get an explicit description of the footprint, which is a sort of hypercube. So you have all monomials like this with the powers in this range, and from this we get, and from this inequality we get the n, and the number of points is just the product of these di's. Okay. So maybe you are asking, but why did you think about choosing these conditions? These conditions appear in several unknown codes. For example, Reed-Solomon codes, Reed-Muller codes, affine cartesian codes, some codes that I had previously worked with together with Iran Lopez and Gretchen Matthews, which we call the decreasing Marquis curves, and among others. Okay, so this is maybe it seems artificial, but it's not. So we describe further properties of the polynomials in the case. Of course, so for all I, the degree of Gi as a polynomial, xi is di. And if you take a point in x, then alpha I is a simple root of, you take Gi, you replace here alpha into alpha I minus 1. Okay, so this is a polynomial xi, so alpha I is the simple root of this polynomial. This will be important in the next slide. As a corollary, you can prove that this polynomial for any I has di distinct roots in F2. So anyway, okay, to calculate to determine the dual, maybe in the last 8 years, something like that, there's a method that uses the so-called indicator functions for the polynomials when you work with evaluation codes. So an indicator function for a point P, an indicator function for a point P is just a polynomial which evaluates in one at P, 0 in the other points of X, and all the monomials which appear in F belong to the footprint. This last condition is not really a big deal. So this is the definition of indicator function. So using this in the method which was developed in several papers, especially by Lawrence and we were able to determine the indicator function of P, which is exactly this polynomial. So this is actually a polynomial because alpha I is a root of this polynomial. Okay? And alpha I was a single root of this polynomial. So this is a non-zero element. So we may determine the leading coefficient of the leading monomial of Fp is this μp, which you can determine using this equality. Okay? And an important thing is that, of course, this is the polynomial of degree x1 to d1 minus 1, and so on. So the leading monomial of this indicator function is this monomial. So the leading monomial does not depend on P. So this was important to use the method I said before. Of course, I had to make some adaptations of the methods, elements, but this was important to prove this theorem. So CAV, the generalized monomial code, where you choose a subset of the monomials of the A. So let P now be a set of monomials, also in the footprint, such that the cardinality of this subset B, together with the cardinality of the chosen set A, is the cardinality of all the monomials in the footprint. And if you take any monomial in set A, and any monomial in set B, of course, you can make the product, you can consider the class of the product. From Buchberger's result, you know that the class of the product must be a linear combination, is written uniquely as a linear combination of the monomial of these classes of monomials, footprint, and I want that this product has 0 coefficient in this class. So this is the class of that leading monomial of the indicator function. If you think this the footprint as a hierarchy or a cube or a rectangle, so this would be the monomial that would be in the upper right corner, so to speak. So I don't want this the class of this monomial to be here, and I write this product as a linear combination. If this happens, then the dual of the code that we have constructed is also a code of that form. Okay? And we know exactly who this V prime is. So it's this n double of elements of FQ. And of course, here is resuming, which appears under the leading coefficients of the indicator function. Okay, and we also in the result about this the intersection of the students called the home, and we have this resulting dimension of home, which is m atoms. Okay. So, but maybe you will think, okay, but did you choose this just to prove the theorem? Because it seems a little bit artificial. but actually it is not. And I also I presented a condition where a situation where you always have that condition, where that condition always holds. For example, assume that your monomial order is a graded order, meaning that when you want to know which monomial is the greatest, first you look at the degree. If a monomial has a degree greater than the other, it is already greater than that. So if it's a degree, so you have some other way to decide. So assume that this monomial order is a graded order. And let's not choose A to be any subset of the footprint, but let's choose A to be this type of set of monomials. You take all monomials with degree up to T. Okay? Then, if you take P as this set, will be actually a set of monomials. You can rewrite this like this, monomials, which have the up to this number. So this is just this set written. And then we can prove that B satisfies that hypothesis of the theory about the cardinality and about that property of the when you take two monomials, multiply, you take class. Okay, so this happens. So this is, let's say, a class of for examples where those conditions hold. The paper has more results, but I don't have time, so I thank you very much for your patience.
Thank you very much, Cicero. Any comment, questions?
Yes, sure. Thank you for the very nice talk. So I think, well, I've done this question to be private, but I think let's share. So I really like the fact that you have a condition on the ramp of the intersection of the dual codes. So do you think it's feasible to find potential dual codes, or on the other hand, side of the spectrum codes for which the intersection with the dual
What?
with your principle should be useful to find self-dual code. So you have
Yes.
looked into that, or on the other side, the ones who have the LCD, I think they're called, have triggered intersection.
Yes, yeah, I give some examples in the paper which may need. I thought about this, but since I didn't have, let's say, an immediate or quick corollary, I didn't write it, but I did some examples which I put in the paper that may lead to this. This is something that, yes, I think we can think about this. We can think about this. It's let's say a prototype of a result would be to choose certain subset A and then B like this, which you already know that code would be LCD or SO2. Yeah, it's. I think it's very possible.
Any other question?
Yeah, my question is, you needed you had a condition because you want the footprint to be very simple, like just X height of the body. But is there another like the condition that could you give it that? Because yeah, if the footprint is that way, it's much easier to.
Yeah. Yeah. So this actually, this paper started exactly with this. Thinking about this, because when you have this footprint with this big box form,
Yeah.
it's easy, but I only had seen this big box when you work with affine cartesian codes. But then working with Iran and Gretchen in these decreasing codes, the big box appeared again. Yeah, first we chose a certain order. The footprint was something irregular, let's say. But then we chose another order, like in the middle of the paper. We had to rewrite everything. And then the footprint became a box. And then I said, so yeah, maybe, there are. So I started to look, and I think that this is a nice characterization, the most general that I think that can be done to find this box thing. But out of this shape, say, it's difficult.
Any other question? Yeah, so can you go back to slide 11? Yeah, this one. So this H is the parity check matrix, N minus the quantum. Yes. The dimension, yeah. So this is the parity check matrix for your book.
Yes.
So
Yes, this is really not a big deal, but I did put this because I wanted to do examples because I had seen previous some results about this. Someone that had a way to determine the dimension of the object. It was so complicated using applications. Maybe you have seen this paper, Okay, but I mean, there are simpler ways, I think. So this was really not a big deal. It was simpler, and you can actually find this the way I did. You can actually find this. Almost find this. So that's why I put it in, because it was simpler than the other criteria that was published in IEEE.
Any other question? Thank you very much, Cicero.